Hi everyone, this is Hossein, and today we're exploring a topic in the field of biomaterials and, of course, additive manufacturing, more importantly. In this episode, we'll be talking about an article that focuses on laser-based additive manufacturing of magnesium. So, as you know, in the biomedical sciences, magnesium alloys, with their unique biodegradability and the ability to mimic the mechanical behavior of bone, are making waves in the fabrication of medical implants. So this article highlights how laser powder bed fusion, which is a method for fabrication, a method for 3D printing fabrication, is used in the creating customized biodegradable scaffolds for orthopedic and also other medical applications. So sit back and let's dive into it. This review article that was published in December 2022 titled Laser-Based Additive Manufacturing of Magnesium Alloys for Bone Tissue Engineering Applications from Chemistry to Clinic, as you see. I was one of the co-authors in this review and it was a comprehensive review, let's say. So I highly recommend that. Go to MDPI or Google Scholar, search it. And this is a very good review, by the way. In this article, we have an introduction, we have laser powder bed fusion, one method for additive manufacturing, as I said, which is the richest section of this article. We'll have a section about properties of this method for magnesium implants and corrosion behavior, as you see, and biocompatibility of alloys. And at the end, we have conclusions, challenges, and future perspectives. So let's go back in the magnesium history, because let's start to read the article. So we are starting from the introduction, the first part of the article. Abstract is when you don't want to read the whole. So in the cases you want to read the whole paper, the reading abstract is not necessary, or the moments that you are forced to read the whole paper. The reading abstract is also not necessary. So at the beginning, introduction, the article said, it has been proven that magnesium alloys are a viable degradable biomaterial that can be used in orthopedic surgery, respirology, cardiology, and urology. So I think we should talk about a little in terms of the history of magnesium in the medical sciences. It could be useful to comprehend the background of the term and the concept, and to making concept correctly in our minds. So magnesium's roots trace back to the ancient civilizations. The term magnesium actually is derived from Magnesia, a region in the Thessaly, Greece, where mineral deposits containing magnesium compounds. As you see, Magnesia, a city in Greece, were the first city that magnesium. This is a travel services or something like that, travel guide website. So if you want to buy pure ancient magnesium, let's go travel to Magnesia. And by the way, people, even people before, they understand elements and compounds, and they recognize that certain minerals from Magnesia had distinct properties, particularly those related to healing and overall well-being. For example, magnesium salts, which you might find in mineral baths. Though these practices weren't biomedical implants in the modern sense, they do reflect how ancient people appreciated magnesium's potential to influence health. Then in late 19th and early 20th century, we have pioneering surgical experiments. One of the key advantages, or maybe one of the most advantages of magnesium, is that it gradually dissolves in the human body in vivo situations, which can help avoid long-term complications. It means no permanent metal left behind. Around 65% of our body's magnesium is stored in our bones, so it's already essential for bone health. Another plus is magnesium's elastic modulus, which is closer to that of natural bone compared to metals like stainless steel or titanium. That reduces the stress shielding effect between our bone and the implant. And this actually can help bones maintain their strength over time. Stress shielding's definition is a phenomenon that occurs when a bone's density decreases after an implant is placed in it. So, if the modulus of an implant was so higher than the natural bone, we have the phenomenon of stress shielding. Because of that, the implant reduces the amount of stress on the bone, which causes the bone to remodel, and that's a bad effect. But magnesium alloys reduces that effect. So we have that, and it's also worth noting, while magnesium breaks down naturally, its corrosion can sometimes release hydrogen gas, may form some pockets in surrounding tissues, and we have some methods to prevent that. I will address these problems shortly. Despite its promise, most magnesium alloys are still made using pressure die casting, and they're tough to form at room temperature. Traditional production methods such as casting, forging, and powder metallurgy can be slow, energy heavy, and maybe not really flexible for producing intricate patient-specific designs. So we have advanced manufacturing methods that in these situations could truly unlock magnesium's potential in our bone repair. And you can see the table, a comparison of magnesium implants properties with the other biomaterials, and we can see that magnesium implants sit somewhere between bone and traditional metals like stainless steel and titanium when it comes to its mechanical properties. For instance, cortical bone has a Young's modulus range, I see, between 7 and 30 gigapascal. And magnesium is listed at around 41 gigapascal, significantly lower than 193 gigapascal of stainless steel and or the 240 gigapascal of cobalt chromium alloy. This closer match to bone stiffness reduces stress shielding, as we talked about, meaning bone remains more engaged in load bearing and less likely to weaken over time. On the other hand, magnesium's yield strength and tensile strength as well fall somewhat and somehow below those of metals such as titanium, suggesting that while magnesium implants can handle moderate loads, they aren't quite as robust under extreme stress. So magnesium's compression strength is often enough for certain orthopedic applications where complete mechanical support isn't required long term. You should consider that fact and combine that with magnesium's ability to degrade naturally in the body, and you get an attractive compromise. Lower stiffness compared to conventional metals, plus the added benefit of avoiding permanent implants. However, these comparatively modest strengths also underscore the need for careful engineering, though allowing coating or structural design to ensure magnesium implants can safely bear forces, and additive manufacturing as a savior in this field. Here's why. It can produce designs that simply aren't possible in older manufacturing methods, and it opens the door to creating novel biomaterials. On the top of that, AM is more energy efficient and generates less waste. And we can optimize, engineers can optimize that and can reduce a part's mass even further, which is especially interesting for a metal like magnesium that's already quite light. Large surface areas can be built into these designs to promote better cell attachment, growth, and bone regeneration, or to act as electrodes that facilitate certain reactions. When magnesium does degrade in an aqueous environment, it produces magnesium hydroxide and hydrogen gas, basically reflecting the metal's anodic reaction in combination with water's cathodic reaction. This means that over time, a magnesium implant can safely break down inside our body. That's interesting. But the manufacturing and design process need to be carefully managed to control that degradation rate. That's precisely where the flexibility of additive manufacturing comes in. So, interesting enough. And AM devices are available. For example, if you are in the US, you'll see university and medical device startups are collaborating on developing 3D printing techniques. Some techniques such as extrusion based are so available in, I should say, in any country. But some technologies, as we see on the title, laser-based additive manufacturing, are more rare. But for instance, in the UK, organizations like Renishaw, known for metal additive manufacturing systems, and various academic groups have ongoing projects to refine technology for orthopedic and dental applications. And Canada also has a growing network between research institutes and universities in the field of additive manufacturing. For instance, University of Waterloo and University of British Columbia are developing AM devices, and they are very in the frontier of that technology. In Iran, extrusion-based technologies, it is available in Mashhad, in Tehran, in Isfahan. They are available in Isfahan University of Medical Sciences, and in Tehran in 3DPL company, in Umid Afarinan company is available in Mashhad, in Iran Honor company is available, and many other universities, for example, Amir Kabir University, for example, Sharif Amir Kabir, they are also available extrusion-based 3D printing in scientific manner. I'm not talking about commercial 3D printing. No, 3D printing in a scientific and in a laboratory. One of the major challenges for magnesium implants lies in their tendency to corrode quickly, and the other is their relatively low bioactivity. So, as a result, before using them as a clinical implant, we should address these two issues, particularly by improving surface modifications. We have a lot of surface modifications methods, and to slow down corrosion and enhance biocompatibility. For surface modifications, this work is happening in the specialized research centers, university labs, or private R&D facilities. And with additive manufacturing, we hope we can create these patient-specific, topological, optimized, and biodegradable MG implants. But another big hurdle is the reactive nature of magnesium powder, which can oxidize or evaporate during processing, requiring specialized printing setups to handle its safety. As you know, magnesium oxidizes so readily, so quickly, that it's used in fire-producing manner, in fireworks. Actually, when I was a kid, I had 100-gram package of Sigma brand magnesium and used most of it for exactly that purpose. But anyway, in the next episode, we'll continue the article, and specifically we'll talk about the role of different additive manufacturing methods in this regard. Please share your thoughts. Take care until the next episode. Thanks for listening.